Hello, students. Last episode, we drove one module, one green box, a few pins, done. Cute, manageable. You could hold the entire thing in your head at once. But here is the reality check. Real chips are not one module. A modern SoC might have hundreds, sometimes thousands of modules, all calling each other, all nested inside each other. And the second you are dealing with something that big, a genuinely important question shows up. Where do you even start? Do you start by describing the whole system and work your way down into the details? Or do you start with small pieces you already trust and build your way up? Today, both answers. This is the top-down versus bottom-up design methodology. And by the end of this video, you will know exactly which one to reach for and when. Let's actually sit with this problem for a second because it's a real one, not a textbook abstraction. Last lecture diagram was one chip, a green box, a few input pins, a couple output pins, simple but real design, hundreds of calling other modules, nested 3, 4, 5 levels deep. If you just start typing Verilog with no plan, no structure, you are gone and end up with an unmanageable mess or versus a design that doesn't even do what it was supposed to do. Here is the good news. This isn't a new problem. An engineer solved it decades ago with exactly two philosophies. Not five, not 10, two. And today we are covering both completely. Here is the big picture before we zoom into either one. Top down starts at the top, the full system specification and work its way down. Specification, then system, sub specification, then functional blocks, then final RTL and gate. You start broad and get progressively more specific. Bottom up is the exact opposite direction. You start at the bottom. Gates are really whatever proven building blocks you already have and work your way up. Gate, then block, then subsystem, and then finally the full specification emerges as a byproduct of combining everything. You start specific and get progressively broader. Same four checkpoints, both direction, just opposite arrow, and that's generally the entire concept in one sentence. Everything else today is just detailed and example. Let's zoom into top down first. Look at that funnel of the on the left. You start white at the top, which is green, full system spec. This is where you write down in plain functional terms exactly what the entire chip needs to do. No implementation details yet, just behavior. And here is a call back. For you, this is exactly the highest, most abstract level from episode 2. Behavioral modeling, you are describing what, not how. From there, that specification gets broken into subsystems. Big functional chunks of the design, each handling one major piece of responsibility. Each subsystem then gets broken further into functional blocks, smaller, more specific pieces, and finally each block gets refined all the way down into actual RTL and gates. Implementable Verilog. The key insight at every step you are refining. You are not designing everything at once. You write a specification, break it into smaller specs, break those into even smaller specs, and you keep going until each space is small enough that you can just write the Verilog for it directly. Let's make this concrete with a real walkthrough. So you are designing a simple calculator chip. You start with the full specification, build a chip that adds, subtract, or multiplies two 8-bit numbers. That's it. That's the whole starting point. No gates mentioned, no wire mentioned. That break down into three subsystems and ALU core to do the actual math. A control unit to decide which operation happens and a register file to hold the numbers. Each of those then breaks down further. The ALU core becomes an adder module, a multiplier module, a mux to pick between operation and a decoder to interpret the operation code. Now you are at a level where you can just write Verilog directly. Now strengths and trade-off. Because neither approach is free on the strength side, you get a clear big picture view from day one because you define the whole system before touching a single gate. It's easier to plan verification early since you know the full spec upfront and it naturally matches how behavioral Verilog gets written. Specification first, refine later. On the trade-off side, low-level details are unknown early on. You don't know yet exactly how the adder will be implemented. When you are still at the specification stage, sometimes lower level blocks don't fit your original assumptions, and that can force a redesign pathway through if a low level constraint clashes with a decision you made way back at the top. Now let's flip it bottom up. Look at the pyramid and notice it's mirrored widest at the bottom. This time, RTL and gate narrowing as it goes up through functional blocks, then subsystem and finally converging at the top into the full system. Now here is how it actually plays out. You start with small, already verified building blocks. Think of this like reaching into a component library and pulling out modules that have already been designed, already tested, already proven to work correctly. You are not designing from scratch, you are reusing your wire those proven blocks together into bigger functional unit. Then you keep combining those units upward layer by layer until eventually almost as an emergent result, the full system appears at the top. Now let's walk through of bottom up. Same calculator, same end goal, completely opposite starting point. This time you start by grabbing existing text, tested module, and adder, a multiplier, a mux, a register modules you already have sitting in the library. Already verified, you wire those together into an ALU core and a control unit. You wire those together into an ALE core and control unit now. Then you wire those together and what pops out the other end is surprise. A chip that adds, subtract or multiplies through 8-bit numbers. Same final specification as before, completely different journey to get there. Strengths, you are reusing blocks that are already tested, which is huge for reliability. It's generally faster when a component library already exists. By redesign and adder from scratch, you have gotten a proven one sitting right there. and it naturally matches gate and switch level thinking from my previous lecture. You are literally starting from the lowest, most concrete level and building upward. Now trade-off on the right-hand side. It's generally easy to lose the big picture view when you are at down assembling small pieces. You can end up with a pile of working modules that don't actually add up to what you need. There is no guarantee the pieces integrate cleanly. Two individual perfect modules can still clash when wired together. And you have to plan ahead carefully for how blocks will connect, and you will hit integration surprises late in the process. Now, the comparison between the top down and bottom up. Starting point top down starts with the full system specification, bottom up starts with existing proven parts. Direction top down goes specification to gates, bottom up goes gates to specification. Best for top-down shines on new unique design when nothing like it exists yet. Bottom-up shines when you are reusing IP or standard shell libraries. Risk. Top-down risk late stage surprises when low-level reality does not match early assumption. Bottom-up risk integration mismatches when individually good pieces don't combine cleanly, and matching back to previous abstraction level video. Top down naturally aligns with behavioral modeling, the highest, most abstract level. Bottom up naturally aligns with gate and switch level modeling, the lowest, the most concrete levels. Notice the pattern. These two methodologies aren't randomly different. They map directly onto the abstraction ladder we already built. That's not a confidence. It's the same zoom in, zoom out relationship just applied to enter system instead of a single circuit. Here is the honest truth. Nobody tells you upfront. Real project almost never pick just one. Most real chips are planned top down at the architecture level. Senior engineer or architect define the full spec and break it into subsystem exactly like we walked through. But then the individual engineer actually building those subsystems. They work bottom up, reusing pre-verified IP blocks and standard cell libraries wherever they possibly can. Because why would you reinvent an adder that a thousand other chips already use successfully? The two directions literally meet in the middle, and here is a tie back to first video. Remember the VLSI design flow, specification to RTL to synthesis to physical design. That entire flow is fundamentally top down in structure. But synthesis and physical design lean on bottom up cell libraries the entire way through pulling proven gate level and transistor level building blocks from a library rather than reinventing them. Top down gives you the roadmap, bottom up gives you the actual brick. Here is your one sentence, one thing to remember. Top down is philosophy that tells you what the system needs to accomplish, breaking that goal down piece by piece. Bottom up is a philosophy that tells you what you are actually doing going to build it out of real existing trusted components. Neither one is the correct way to design hardware. They are not competitors, they are two different tools in the same toolbox and pretty much vary every real design you will ever touch uses both at different stages for different reasons. So, quick recap top down starts broad and refines down to gates. Bottom up starts with proven parts and builds up to the full system. Real design blend both, and this whole framework mapped directly into the abstraction level from my previous episode. Two direction, one goal, managing complexity in a design too big to hold in your head all at once. Next episode, we are tackling something that trips up literally everyone the first time they see it in video. The difference between a module and a module instant. Quick preview of the vibe. A module is like a chip dataset. It describes what an AND gate does, but it doesn't physically exist yet. An instant is what happens the moment you actually place that chip on a board. It's real. It's there. And you can play the same datasheet down 5 different times to get 5 different, completely independent real gates. Same confusion people have with classes and objects in programming. Except this time it's actual hardware. Subscribe, stay in the playlist. I will see you in the next video. Thanks for watching. Share with your friends this video if you enjoy learning with MKG Online Study and e-learning platform.